Greetings, everyone. Today we're going to kind of do the opposite of what we've been doing the last few days. The last few days we have been adding vectors together, two or more vectors, and finding the resultant, the net effect of those vectors. Today we're going to take a vector and break it apart into its components. And so here's an example. You walk 15 meters at 35 degrees west of south. How far west and how far south did you walk? But like every vector problem, the first step is to draw a good vector diagram, and the math will lead from there. Now I'm going to draw one to an internal scale within my PowerPoint. You guys will just sketch vector diagrams and then use the trig to find the answers. So let's start out by drawing the 15-meter vector at 35 degrees west of south. These are our crosshairs. West of south would mean that we rotate to the west from the south. So there's 35 degrees west of south. And there's our 15-meter vector. And since this is a displacement vector, it's in meters, I'm going to call that d. Okay, if we have a velocity vector, we would call it v. Okay, so d for displacement. Now, I want to know how far west and how far south we walked. And I want to represent that on my vector diagram. So if I start out with how far west I walked, if this is where I actually went, we could draw an arrow here to represent how far west I walked. Notice it starts where I started, and then it goes off to the west. I'm going to call that d with a subscript of x. Okay, x is horizontal, remember. It's a horizontal displacement. And then how far south did I walk? Well, we could start here and complete the vector diagram. So notice I'm walking west and south, so that's the way the arrows point. Again, these are not triangles that we're drawing, these are vector diagrams. If they have directions associated, must be drawn with arrows. And I'm going to call this one d sub y. Y is vertical, up and down, so horizontal and vertical parts. Now, as you look at this vector diagram, hopefully you see the trig that we could do to actually figure out what dx and dy are. First of all, we need an angle inside of our vector diagram. Since this is 90 in this quadrant, inside of the triangle would be 90 minus 35 degrees or 55 degrees. So that's a 55-degree angle. So if I wanted to find dx, notice that dx is the adjacent side to the angle, and I know the hypotenuse. And of course, there is a right triangle trig function which relates the adjacent side, the hypotenuse, and the angle. That would, of course, be the cosine function. Cosine of 55 degrees is adjacent side over hypotenuse. The cosine of 55 degrees is the ratio of the length of the adjacent side to the length of the hypotenuse. And if I want to solve this for dx, I just have to remember that this horizontal line means divide. So to move the 15, I have to multiply both sides by 15 meters. And of course, I flip to what I want to solve for because I like it that way. So 15 meters cosine of 55, making sure, of course, that your calculator is in degrees. Notice we have 2 sig figs in both of our numbers. So we're going to have 2 sig figs in our answer, and we need a direction. And since we use north, south, east, west in our problem, we'll use the cardinal directions in our answer. And so dx becomes 8.6 meters west. So that's how far west I went. To figure out how far south I went, there's really 2 methods. One of them's kind of sloppy, and that would be using the Pythagorean Theorem. I say that one's sloppy because I would have to use what I just found. And if I made a mistake here, I'd double my mistake there. So it's always best to just use givens. Okay? And in that case, I can do that because dy is the opposite side to the angle. Of course, there's another trig function which relates the length of the opposite side to the length of the hypotenuse and the angle. That would, of course, be the sine function. Sine of 55 degrees would be the ratio of the length of the opposite side, d sub y, to the hypotenuse. And again, to solve for d sub y, that's dividing, so we have to multiply. Calculator in degrees, 2 sig figs in both numbers, 12 meters, and a direction of south. So here's the answer to our problem. Right? We wanted to figure out how far west and how far south we walked if we walked 15 meters at 35 degrees west of south. So if you notice here, notice these 2 vectors are drawn head to tail. And as we've learned over the last few days, head to tail construction of a vector diagram means addition. In other words, you could go 8.6 meters west and then 12 meters south and end up doing the same thing as if you went 15 meters at 35 degrees west of south, or even 55 degrees south of west. So these are the 2 vectors which added together make up our resultant. And those 2 vectors actually have a special name. They are called components. Okay, components are the 2 vectors that are added to give the resultant. So you might call this the x component of the displacement, or more appropriately perhaps, the horizontal component of the displacement. And d sub y is the y component or the vertical component of the displacement. And so our components. And in fact, these are a special set of components. Well, they're special because they're the ones that I wanted in the problem because of how I stated the example. But generally speaking, you're going to see that we are going to find components that are like this. And what's special about them? Well, the angle in between them is what's special. West and south are, of course, perpendicular to one another. So these are known as perpendicular components. Kind of a circular definition. These are components that are perpendicular. Because there's an infinite set of components. I don't know why I did that. Back here. Okay, there is an infinite set of components. Okay, I could draw one from here down to here and then back over to here. And that would be a set of components, but they wouldn't be perpendicular to one another. Now, why are perpendicular components important? Why do we look for perpendicular components in general? Well, consider this diagram here. Okay. If I walk 15 meters at 35 degrees west of south, I end up down here. But let's say if I walk west. If I walk west, how much do I change where I am north and south, perpendicular to west? Of course, I don't change it at all. I could walk west or east for that matter and not change where I am north and south. Likewise, when I walk south or north, I don't change how much I'm walking east and west. So perpendicular components are important because they are independent of one another. That's nice because that means they don't affect one another. So unlike some components at a weird angle, which would have both horizontal and vertical parts, horizontal and vertical, perpendicular, are always independent. And we're going to see this over and over as we go through things this year. It's why we tend to break things up into perpendicular pieces, perpendicular components, because they don't affect one another. And this process in mathematics has a special name. It's called resolution. So we are resolving vectors into their perpendicular components, is the fancy name, or fancy way of saying that. Resolution is the technical full word. We are resolving vectors into their perpendicular components. Now, let's generalize the process here. The first thing we did was we drew the resultant. You don't have to draw it again, of course, it's there. Then we drew the horizontal component, and we didn't just draw it anywhere. We started it at the tail of the resultant. Then we finished the vector diagram by drawing the vertical component, starting at the head of the horizontal, so that we had vector addition. So we're adding up the two perpendicular components. And then we did trig to figure out what they actually were. But it's important to actually at least sketch the diagram. Again, mine's drawn to a perfect internal scale. But when you do this on a worksheet, you could just sketch these out. And you need to see the diagram, because otherwise it's hard to do the trig. Which is the cosine? What's the sine? What direction is it going? All of that stuff. But if you draw a careful vector diagram, that becomes much easier. Now let's do a second example. This one says resolve a 50 meter per second velocity at 120 degrees into its perpendicular components. So we're using the technical math language here of resolution. Okay? You'll notice this doesn't have north, south, east, and west, and that's going to affect how we're going to name things in this problem. Now, 120 degrees is using counterclockwise notation. That means we start at the positive horizontal is 0, and we go around, we rotate around 120 degrees. So that would put us 30 degrees into the second quadrant. So there's a 50 meter per second velocity at 120 degrees. If we were using north, south, east, west, this would be 30 degrees west of north. But we're not using north, south, east, west, so we have to use the way the calculator thinks, counterclockwise from 0 notation. Notice here I'm going to call this v. Why? Because it's a velocity. How do I know it's a velocity? Well, it told me it was a velocity, and it's in units of meters per second, which are velocity units. Okay, so v for velocity, d for displacement. So let's follow our process. Step 1, draw the horizontal component, starting from the tail. It's actually step 2. We've got to draw the resultant first. Right, so notice v sub x. This is the horizontal component of the velocity. Then draw the vertical component starting from the head of the horizontal. So in that case, that's going to be up. So this is the vertical component of the velocity. Now, if we're going to actually find these, again, we have to do some nice right triangle trig. We need an angle inside of the vector diagram. That would be 180 minus 120, which would be 60. Put a 60 in there. Now, yes, this is one of those special triangles. You might know the sine and cosine of a 30, 60, 90 triangle. You may know the ratio of the sides and things like that, but I'm going to work this all out as if we don't have those, but you'll see them pop up as we work. So if I want to find Vx, Vx is the adjacent side. We know the hypotenuse. So we are, again, going to use the cosine. Cosine of 60 degrees is the ratio of the length of the adjacent side, V sub x, over the length of the hypotenuse, 50 meters per second. Again, to solve for Vx, we multiply. And here's where you might know that the cosine of 60 is 1/2. So 50 times 1/2 is 25 meters per second. But we have to be careful here. This is a vector. Okay, these components. I mean, you did draw an arrow. And unlike the last problem, we don't have north, south, east, west. And you never want to superimpose cardinal directions onto a problem if it's not part of the problem. Okay? So there's a couple other ways we could name this. We could say at 180 degrees, because it's pointing out to the left. But there's an easier way to do this. Once we put the x as a subscript, that means we're talking about the horizontal component. And there's only two directions that it could be horizontally. It could point to the left, or it could point to the right. And as we saw last unit, when you're in one dimension and you only have two choices of direction, the easiest mathematical way is just calling them positive if you're to the right or up, and negative if you're to the left or down. So to put a direction on this, we're going to make it negative 25 meters per second. Okay? And again, the negative should tell us, oh, it's to the left. It's horizontal because of the x, and it's to the left. And then we don't need any words at all. Now, there's a couple different ways we could figure that out.
Coach for Column D, if you're in the building, please call 2300. Coach for Column D, if you're in the building, please call 2300.
Hope you enjoyed that announcement. One way is to look at your diagram. And this is why we draw vector diagrams. We don't draw triangles. Look at the arrow. It's pointing to the left. To the left is negative. Another way is to think of the quadrants. If you've been trained well enough in math class, we're in the second quadrant, and in the second quadrant, x's are negative. The third way is to let the calculator know what quadrant you're in so that it knows whether the x's are positive or negative. Now, in this case, if we type in to the calculator 50 meters per second or 50 cosine of 60, the calculator actually thinks you're over here. You're in the first quadrant. Because remember, the calculator uses counterclockwise notation, so it thinks you've only rotated through 60 degrees. So if you want the calculator to know that you're in the second quadrant, you could use 120 degrees. 50 times the cosine of 120, if you punch that into your calculator, will automatically give you the negative sign. Right there. Because then the calculator says, hey, we're in the second quadrant, x's are negative. So this is kind of the more mathematically sophisticated way of doing that. Although, one little thing here that's important. If you're going to use this mathematically sophisticated method, you must draw the horizontal component first, and then the vertical. If you do vertical and then horizontal and try to use this, it's going to make your answers backwards. Okay, so if you want to be mathematically cute about it, draw the horizontal one first, and then you can use the angle from 0. So let's find the vertical component of the velocity. That's going to use a sine function since it's the opposite side. And the sine of 120 degrees, just going to use that right away, is the ratio of the length of the opposite side to the length of the hypotenuse. Multiply by the hypotenuse, plug it in, and you get a Vy of 43 meters per second. And notice here the calculator has spit out a positive answer. And since we're using the 120 degrees, it's trying to tell us the direction. We are talking about a vertical component, and therefore a positive vertical component must be up. So notice here, we can use positive and negative when we make these perpendicular components because each one is one-dimensional and therefore only has two choices for direction. And this is what we'll do quite often here when we're doing problems where we're using counterclockwise from 0 notation instead of cardinal directions. You want to make sure not to mix the two, because if you had written negative 25 meters per second west, Well, technically that's like a double negative. Negative west would be east. So you either have to use one or the other, okay, never both. So how do we again figure out whether it's positive or negative when we're using counterclockwise from zero notation? 3 ways. Look at the arrow. If you draw a vector diagram here, you can tell that it's either left or down is negative, right and up are positive. So that's another good reason to draw vector diagrams, not triangles. Look at the quadrant it's in. Second quadrant, x's are negative, y's are positive. And the third way is use the angle measured from the positive horizontal. Counterclockwise notation, as the MOP guy would call it. But in order to do that, you must draw the horizontal component first. And like I have here, and like I told you to do previous. So, I hope you enjoyed learning how to resolve vectors into their perpendicular components and a couple of different ways of naming them. And you're going to now do a worksheet that is very similar to that, and of course, some MOPs.